Yeah.
Okay. Anyway, now you can share. You have the right to share directly.
Yeah. Perfect. Yeah. So let's share screen.
Very good. Okay. Very good. Let's wait. Almost nothing. 1 minute. Let's wait a little bit so you can.
Yeah, so I will try to connect also with my iPad so that I can add some pictures.
I'll let you decide what you want to do. Now you are here, and that's fine.
Thank you. Okay.
Okay. Okay.
Okay, well, maybe tomorrow. Yeah.
When you're ready. All right.
Yeah. Okay, so let's do with the slides only. Yeah.
Very good. So to everybody, it's our pleasure to welcome Andrea Mondino from Oxford, who will speak about what I should call a synthetic version of a Ricci curvature and consequences. Andrea, if sometimes questions are asked on the chat.
Sure.
So
okay. So I will keep an eye.
I will be looking at the chat regularly and tell you if there is any question.
Thank you very much.
And some questions may be asked by people in the room here. We are not that many, but still. Okay, please.
Yeah, so please feel free to interrupt me at any time and say, if I don't see the chat, just shout and I will stop. And
yeah, don't worry. Okay.
Okay. Can I start?
Yes, please.
Perfect. Okay. Thank you very much to the organizer for this kind invitation. It's a great pleasure to give this mini course about, say, synthetic notions of Ricci curvature lower bounds. So the plan of these lectures is that I will start with some from basics to, let's see where we will arrive. So today I will start with some introduction to curvature and convergence of smooth Riemann manifolds. Here I will go I will start from really the basics, but I will go quite quick because I know that last week there's been some introductory course in Riemann geometry, and then there is the course by Cristina Sormani about convergence of manifolds. And so here I will just give some, just fix some notation, but we'll refer to the other courses. And then already today, we are going to see the definitions and stability of synthetic notion of lower Ricci curvature bounds. And then in the next lectures, we will see some analytic and geometric properties of these no-smooth spaces satisfying lower Ricci curvature bounds. And then in the final part of this journey, we will come back to the smooth world and see how these say non-smooth notions can be useful in order to prove some results which are new even for smooth Riemann manifolds. Okay, so we start from smooth, we go to non-smooth, and then eventually we will come back home to smooth Riemann manifolds. Okay, so that's the plan of our journey. So let me start with something that we all know from second year, but just to fix some notation. So from the Gaussian curvature of two-dimensional surfaces. So we are given a two-dimensional Riemannian surface sigma. So denote with nabla the Levi-Civita connection of sigma endowed with the Riemannian metric G.
Andrea, your slides are frozen on the first page.
Oh, on my okay.
Maybe
sharing is paused. Okay, right. Sharing is paused. Bring your shared window to the front. Let's see. it's better.
We're still on the first page.
Okay.
Maybe you should restart sharing.
Yeah, so maybe stop sharing and then we'll restart. Now it's better. Yeah.
Yes. Thank you very much.
Okay. Thank you very much. Yeah. Okay. So here was just the slides about the plan of the journey, but you got it. So we can go to the Gaussian curvature of a two-dimensional surface. So we are given sigma, a two-dimensional surface, endowed with the Riemannian metric G. We denote with nabla the Levi-Civita connection of sigma with metric G. Now, given some point P, we consider a coordinate basis, Ex, Ey, then the X, then in the Y, which is coordinate basis of the tangent space of sigma at P. And as you know, the Gaussian curvature at P is defined as follows. So you consider the first vector of the basis, and you consider the covariant derivative first with respect to Ey, and then with respect to Ex, and then you symmetrize and you change sign. And this is a tangent vector, and you take the scalar product with the other vector of the basis. This gives you a number, and then you normalize it with the determinant of G with respect to this basis in order to have a number which is coordinate free. This is the classical Gaussian curvature. Of course, as we all know, if the surface sigma is isometrically immersed in R3, then the Gaussian curvature is nothing but the product of the principal curvatures at P, which is nothing but the Jacobian of the Gauss map at the point P. Now, some examples. Of course, the Gaussian curvature of the Euclidean plane is 0. The Gaussian curvature of a two-dimensional round sphere of radius r immersed in R3 is 1 over r squared. And the Gaussian curvature of the hyperbolic plane, here I'm just recalling one of the models with the half plane with such metric, is -1. Okay, so this is Gaussian curvature of two-dimensional surfaces. So it's second year of university. Now let's do something of the third year. So what about sectional and Ricci curvature of Riemannian manifolds? So we are given an n-dimensional Riemannian manifold. How to define the sectional curvature using the Gaussian curvature? So we fix some point P in the manifold, and we fix some two-dimensional subspace pi in the tangent space at P. Let's say that this two-dimensional space is the span of vectors E1 and E2. Then what we do, we consider the two-dimensional surface obtained by exponentiating the geodesics tangent to pi just for a small time. So this sigma pi is the exponential based in P of the plane pi intersected with a small ball. And what I was saying is the surface obtained by considering by shooting all the geodesics starting at P tangent to pi up to some small length epsilon. Now one can check that for epsilon small enough, sigma pi is a smooth two-dimensional surface, so one can induce the Riemannian metric over sigma pi and compute its Gaussian curvature. And by definition, the sectional curvature of M at the two-dimensional plane pi is nothing but the Gaussian curvature of this surface sigma pi at the point P. Okay. So this defines the sectional curvature using the Gaussian curvature. And once we have the sectional curvature, we can define the Ricci curvature of the manifold M at a vector V as follows. So if the vector V is equal to 0, it is the null vector, then by definition, the Ricci curvature is equal to 0. If instead the vector is non-zero, then we normalize it. So we get a vector of norm 1. And we complete it to an orthonormal basis of the tangent space. So U1, En minus 1, normalized V, let's say that is an orthonormal basis of the tangent space. And in order to have the Ricci curvature, what we do, we consider the plane VE1, this gives a plane, and then we have the sectional curvature at that plane. Then we sum up the sectional curvature of the plane VE2. Then we sum up the sectional curvature of vector VE3 and so on. So this gives a kind of a trace of the curvature. And this is by definition the Ricci curvature. And in order to have, say, a tensor, it is useful to multiply this by the norm squared of the vector V. One can check that with this definition, the Ricci curvature is a quadratic form on the tangent space. And we're going to denote it so with the Ricci curvature and with sec the sectional curvature. Now, what so we're going to use a lot curvature bounds. I think we say this was already treated in the last week courses, but let me just fix some notation. So we say that that sec is bounded below by k, where k is a given real number, if for every point and for every two-dimensional plane in tangent space at P, it holds that the sectional curvature at the point P and at the plane pi is bigger or equal than k, or respectively less or equal than k, if we say that the sectional curvature is bounded below by k. So sectional curvature bounded below means bounded below by that constant on every plane at every point. What about bounds on the Ricci curvature? Now, the Ricci curvature instead is a quadratic form. So what do we mean with Ricci curvature bounded below or bounded above? So we say that the Ricci curvature is bounded below by a constant k if the quadratic form Ricci minus k times the Riemannian metric G is non-negative definite at every point P. So this means, so with the quadratic form non-negative definite basically means that all the eigenvalues of the Ricci with respect to the metric G are bigger than k. And if instead you say that the Ricci is bounded above by k, you mean that Ricci minus kg is non-positive definite for every point. Okay, so this is just to fix some notation about what we mean with the upper and lower bounds on the Ricci and on the sectional curvature. So it is very useful to have in mind some model examples, because we are going to compare the geometry and the analysis with such model examples. So of course, the model example of zero curvature is the Euclidean space. So the n-dimensional Euclidean space is of course sectional curvature equal to 0 and Ricci curvature equal to 0. The model space in positive curvature is the round sphere. So the sectional curvature of the n-dimensional round sphere of radius 1 is 1, and the Ricci, since I remember that we are summing up the sectional curvature on n-1 planes, the Ricci curvature is equal to n-1. The model space in negative curvature instead is the hyperbolic space, and which has sectional curvature -1 and Ricci equal to -n-1. Okay, so up to here, I think that we are all very familiar with the material. And now let me just motivate what comes next with say with a basic question of a beautiful section of Riemann geometry, which goes under the name of comparison geometry. So the basic question is, given a smooth Riemannian manifold, if we assume some upper or lower bounds on the sectional or on the Ricci curvature, what can we say on the analysis or the geometry of M? So what is classical is that upper and lower bounds on the sectional curvature are strong assumptions with strong implications. Here, there are a lot of theorems, a lot of beautiful results. Here, let me just mention two fundamental results, very classical. The first one is the Cartan-Hadamard theorem, which says that if a Riemann manifold has non-positive sectional curvature, then the universal cover is diffeomorphic to Rn. This is a very, very strong topological information, because it means that the old topology of the manifold is encoded in the fundamental group. So once you know the fundamental group, then you know all the topology of your manifold, once you know that it has non-positive sectional curvature. So Okay, so for instance, if you have a manifold whose universal cover is not diffeomorphic to Rn, you know that you can never put a metric with negative sectional curvature. Another fundamental result in about sectional curvature bounds is the Topogonov-Triangle comparison theorem, which basically tells that in positive curvature, the triangle made by geodesics look more fat than the geodesic triangle in Euclidean space. And in negative curvature, instead, the triangle made by geodesics look more thin than the one in the Euclidean space. One can make this notion of fat and thin rigorous using only the distance function. And this is a complete characterization of sectional curvature bounds in for Riemannian manifolds. And so this was the starting point of Alexandrov geometry. Indeed, Alexandrov realized that one can take, say, this smooth characterization of sectional curvature as a definition for sectional curvature bounds in a metric space. And here started the beautiful topic of Alexandrov spaces, which are non-smooth spaces, so metric spaces, with upper or lower bounds on the sectional curvature in a synthetic sense using the geodesic triangles. Okay, so this was a super brief sketch about about this huge and beautiful section, which is Alexandrov geometry. And now, what about, since this course is about Ricci curvature, let's see what happens in Ricci curvature. So we have seen that for sectional curvature, both upper and lower bounds are very strong. They are meaningful and they give beautiful results. Now, what about upper bounds on the Ricci curvature? Actually, it turns out that upper bounds alone on the Ricci curvature are somehow too weak assumptions for geometric conclusions. Here, let me just mention a beautiful result by Lohkamp, which improved the previous result by Gao Yao and Brooks, which tell us that any closed manifold of dimension at least 3 carries a metric with negative Ricci curvature. So while for sectional curvature, knowing that that a closed manifold admits a metric with negative sectional curvature gives a lot of topological restrictions, instead, knowing that the manifold admits a metric with negative Ricci curvature gives no restriction, just because any closed manifold of dimension at least 3 will admit a metric with negative Ricci. And actually, you can make the upper bound on the Ricci as negative as you wish. Okay. And instead, the lower bounds on the Ricci curvature give a natural framework for comparison geometry from below. So if you're interested in lower bounds on some curvature, well, lower bounds on the Ricci curvature really give a lot of information on the geometry of your space. For instance, so there are plenty of results, and we are going to touch some of them during these 4 lectures. Here, let me just mention one more in detail and then just mention a few other names. So one key result in lower Ricci equal to bounds is the Bishop-Gromov volume comparison, which permit to control the volume of metric balls. So here, let me just give the statement for non-negative Ricci. So you have the corresponding statement for Ricci bounded below by any constant just by comparing with the model space. So for negative Ricci, so for non-negative Ricci, you compare with the Euclidean space, which is the model space for 0 curvature. For positive Ricci, you will compare with the sphere of the right radius, and for negative Ricci, you will compare with the hyperbolic space of the correct sectional curvature. Okay, so what happens in non-negative Ricci? So one in non-negative Ricci, one has that the ratio between the volume of the metric ball of radius r in the manifold over the volume of the magic ball of radius r in Rn is monotone, non-increasing. Okay, so you have this function has a monotonicity, and if you know some regularity theory, some geometric measure theory, and so on, once you have monotonicity, you have a lot of informations. You can extract a lot of informations. And in particular, notice that when r goes to 0, then you can just consider, say, exponential coordinates based in x. You see that the magic ball of radius r is very, very close in, say, in any ck norm to the Euclidean ball of the same radius. So you can check that such a ratio converges to 1 as r goes to 0. Okay, so since this ratio goes to 1 as r goes to 0, and it is monotone, non-increasing, in particular, this implies what is known as Bishop theorem, which is that the volume of the magic ball of radius r in your manifold is bounded above by the Euclidean corresponding. Okay, so this is saying that, say, the intuition behind bounds on the Ricci curvature is that a manifold with positive Ricci curvature is, in some sense, smaller than the Euclidean space. In the sense that the volume of the ball of radius r is smaller than the corresponding volume in the Euclidean space. And this kind of smallness is always to be thought as kind of average in all the directions, and is quite powerful, and say, is an intuition that is useful in several geometric scenarios, say, more tricky than this one on the volume. Okay, so this is about Bishop-Gromov. Then, so from Bishop-Gromov, we see that we can control the volume of magic balls. Then one can control also from above the Laplacian of the distance function using the Laplacian comparison. One can control the heat flow using the Liao inequalities. One can control also the isoperimetry of your manifold using the Levi-Gromov isoperimetry inequality. We're going to see more of that in the next lectures. And then one also has some beautiful rigidity theorem, like the Cheeger-Gromov splitting theorem, which says that if your manifold has non-negative Ricci and it contains a line, which is a length minimizing geodesic of infinite length, or in other terms, an isometric immersion of R in the manifold, then the manifold splits isometrically an R factor. Okay, so these are just few of the many beautiful results about lower bounds on the Ricci. Okay, so this is some warm-up in the smooth setting. Now let's gently go to the non-smooth setting, starting by the origins of the topic. So the topic goes back to Gromov, who in the 80s introduced a notion of convergence of Riemannian manifolds, which is now known as Gromov-Hausdorff convergence. So Gromov-Hausdorff convergence is one of the interesting and useful notion of convergence for compact manifolds. If instead you have a non-compact manifold, it is more convenient to work with a pointed version of the Gromov-Hausdorff convergence called pointed Gromov-Hausdorff convergence, which consists in asking Gromov-Hausdorff convergence of magic balls of every fixed radius. So you fix a radius r, and you fix a base point x bar. If you have a sequence xn of manifolds of spaces, you fix some base points xn bar, and you ask that for any radius r, the balls of center xn bar in radius r converge Gromov-Hausdorff to the limit ball of radius r in the limit point x bar infinity. Okay. So it introduced this notion of convergence that I'm not going to recall because it will be done in the course by Sormani. Let me just briefly, in a rough sense, one should think of Gromov-Hausdorff convergence as a kind of uniform convergence of the matrix of the metric D, not G, of the distance function. So it is a bit weaker. So it is a little bit weaker than the uniform convergence of the matrix D, but say as a first approximation, it is a first approximation of that. Okay. So Gromov introduced this notion of convergence, and he observed that a sequence of Riemannian manifolds satisfying a uniform lower bound on the Ricci curvature, and they are of fixed dimension, they are pre-compact in the sense that they admit a subsequence which is converging in this Gromov-Hausdorff sense to a limit space. And actually, this limit space may be non-smooth, and it's a very interesting problem to understand the structure and the properties of these non-smooth spaces arising as limits of manifold with lower bound on the Ricci. And from now on, I will call these limit spaces of manifold with lower bound on the Ricci limits. Okay, and then the natural question is, what can we say about the compactification of the space of Riemannian manifold with lower bound on the Ricci? And the hope that we're going to see it is well posed, because it will have a lot of interesting consequences, is that studying this compactification is useful to establish properties also for smooth manifolds. So here would say the standard way of thinking is that if we are able to prove some sharp and rigid inequality for non-smooth spaces, like, no, for instance, the diameter. So if we were able to say that non-smooth spaces with Ricci bound below by 1 and minus 1, actually is going to be and dimension n, and diameter always have diameter at most pi, and the diameter pi, if and only if they are special, and this special means we are going to see are spherical suspensions, then what can we infer on smooth manifolds? Of course, we can infer that we still have the upper bound on the diameter, but we can also say something more, because we can say that if if a manifold has diameter close to close to pi, which is this upper bound, then my manifold must be close in Gromov-Hausdorff sense to this spherical suspension or this spherical or this say special spaces. Why? Because one can use a standard argument by compactness and contradiction. So one says, assume that you have a sequence of manifold with Ricci bound below by n-1 and dimension bounded above by n, and assume that they have the diameter arbitrarily close to pi, but they are far away from any spherical suspension. Okay, then by Gromov compactness we can extract a subsequence which is converging. Okay, then we observe that this inequality passes to the limit under Gromov-Hausdorff convergence. So in the end we get a non-smooth space which achieves equality in the inequality. So it has diameter equal to pi. Then we can kick in the rigidity result in the non-smooth setting, infer that this non-smooth space is a spherical suspension, but then this sequence, which was converging to spherical suspension, will be close to spherical suspension. Contradiction. So this is a kind of a standard way of arguing that once one has a sharp and rigid inequality in the non-smooth setting, this will give automatically an almost rigidity in the smooth setting. And often these almost rigidity results are new in the non-smooth setting, even in the smooth setting. Okay, so this was just so if this was a bit too quick, don't panic. We are going to enter into these arguments in the lecture 3, I think. This was just a warm-up, just to motivate why such a setting could be useful also to establish applications for smooth manifolds. Okay. Okay. So as we were saying, these Ricci limits can have singularities. For instance, a cone, it's really an ice-cream cone, can be seen to be a Ricci limit space, or more generally, any convex boundary, any boundary of a convex body in Rn is a Ricci limit space. And actually, the singularities can even be dense on your space. So these Ricci limits can be quite bad, but they have a lot of interesting and structural properties, which makes them quite remarkable. So this was investigated in 3 fundamental papers by Cheeger-Colding in say 97 to 2000. And here, let me just give you a few basic results in the field. So this field is very rich and deep, and also a bit technical if you go in the details. Here, let me just mention a few basic results. So what happens when you study Ricci limit spaces is that you always have a dichotomy. So you have either the collapsing or the non-collapsing scenario. So the collapsing scenario is when the volume of the balls of radius 1 in the base points of your manifold goes to 0. So here you are considering non-compact manifolds. So we are considering pointed Gromov-Hausdorff convergence. And so we have this marked point x bar k for every point in the manifold. We consider the ball of radius 1, and we go to see its volume. If the volume is going to 0, then we say that the sequence is collapsing. An example to have in mind is a shrinking cylinder. So we have a cylinder, and we just shrink its radius. In this way, the Ricci curvature is going to plus infinity if you have enough dimensions, and you are losing dimension in the limit. You are converging to a geodesic. The situation is much more complicated in general, but in general you can prove that if you have this volume going to 0, this corresponds to a loss of dimension in the limit. The collapsing situation is more difficult because when you collapse, you are losing information. Nevertheless, Cheeger-Colding were able to prove a lot of interesting results. For instance, they were able to prove that the limit space is a uniquely defined volume measure up to scaling, and that almost every point with respect to this limit measure has a Euclidean tangent space, meaning that when you look at an infinitesimal level, your space at almost every point, this looks regular. It looks like Rn. But a priori, from their work, the dimension of this Euclidean tangent space may vary from point to point. And it was actually a conjecture that it doesn't. But okay, now these points with the Euclidean tangent space are called regular points, and the complementary is called singular set. Okay, so this was the collapsing situation. Now, in the non-collapsing situation, you have even more results. The non-collapsing situation corresponds to the case when the limit of the volume of the balls of radius 1 centered in x bar k is bounded below by a strictly positive constant. This case is easier in the sense that you have more information because you can exploit better the Bishop-Gromov inequality, which gives the monotonicity, and this monotonicity is very powerful for proving structural results. One can prove that the Hausdorff dimension passes to a limit, and one can prove final estimates on the singular set. For instance, one can prove that the singular set has Hausdorff codimension at least 2. So if you have a sequence of manifold with no boundary, then the limit space will also have no boundary as a consequence. Okay, So then there's been some results in between, but let me jump to a breakthrough by Colding and Naber in 2012. We're able to prove that actually the dimension of the tangent space does not change on the regular set even in the collapsed case. Okay, so you can attach to a Ricci limit a dimension, which is the dimension of the tangent spaces almost everywhere. And then there's been some beautiful result very recently by Cheeger-Colding and Naber, who are able to prove that in the non-collapsed case, the singular set, which we said that it has a Hausdorff codimension at least 2, is actually rectifiable. So they proved very fine estimates on the singular set. Okay, so actually one could do a 5 lectures only, and even more, I think 10 lectures just on this slide. But let's pass to the non-smooth setting, the synthetic one. Okay, so the aforementioned approach to Ricci curvature for non-smooth spaces is kind of non-intrinsic point of view, because one is considering non-smooth spaces arising as limits of smooth objects. Okay, so this approach is, we know what is Ricci curvature for smooth Riemannian manifolds with a compactness result by Gromov. We pass the limit and we study the non-smooth spaces which are approximated by smooth manifold with Ricci bounded below. Okay, so this is kind of non-intrinsic because you need an approximation by smooth objects. And as we saw in the previous slide, there's always this dichotomy between collapsing and non-collapsing. In any case, this approach is very powerful for structural properties. So this theory that we saw before is really, really remarkable. So in analogy, it is like defining the Sobolev space as the completion of the infinity functions endowed with the W12 norm. So what is to the question, what is a Sobolev function? With the previous point of view, one should answer, well, it is a limit of smooth functions with respect to the W12 norm. But as we know from Fourier, we know that there is also a completely intrinsic way of defining Sobolev functions without using approximations. So what is a Sobolev function from the intrinsic point of view would be, well, it is an L2 function with the distributional derivative in L2. And actually, this intrinsic point of view is very convenient in PDEs, in calculus of variations, and it is very important to have both the points of view. So the goal of this first lecture is to recall how Lott-Villani and Villani were able to define in an intrinsic axiomatic way a non-smooth space with Ricci curvature bounded from below by K and dimension bounded above by N. And we want this, this class of non-smooth spaces to contain Ricci limits, no matter if collapsed or not. So let me do some spoiler here. So we are going to see that actually we are going to introduce a class of non-smooth spaces which contain Ricci limits. They will not, it will not be a complete characteristic. It will not be a synthetic characterization of Ricci limits. Okay, so the analogy with the Sobolev functions is a kind of motivating, but it's not really must not be taken literally true. Okay, so we are going to introduce a class of non-smooth spaces which a priori are larger than a class of Ricci limits, but they contain Ricci limits. And what we have in mind is to prove some, say, geometric analytic properties and structural properties for this synthetic class, and with the hope that it will be useful also for studying smooth spaces. So with maybe a closer analogy with something that probably many people in the audience know is with more classical geometric measure theory. So in classical geometric measure theory, one wants to study the area functional. So for instance, to solve the plateau problem. So for, let me just say 2 words about the plateau problem. So in the plateau problem, you have a kind of, you have a, say, a codimension 2 submanifold, say a curve in R3 or a codimension 2 submanifold in Rn. Okay, and you ask yourself, how can I fill this curve with a surface of minimal area? Okay, or if you are in higher dimension, can you fill this codimension 2 submanifold with a codimension 1 submanifold having this as a boundary and with minimal area? So if you pose this problem in the classical sense, the area makes sense for a C1 surface or a C1 submanifold. And so you may ask, I want to minimize the area among all the surfaces with that boundary and which are C1. Okay, but then if you know a little bit of analysis and you try to prove that you have a minimizer, the classical way to do it is the direct method in the calculus of variation. So you want to take a minimizing sequence and prove that this minimizing sequence has some compactness, pass it to the limit, and use that the functional is lower semi-continuous to prove that the limit is a minimizer. Okay. Now, the area functional is, of course, lower semi-continuous, is actually continuous under C1 convergence, but having a bound on the area is not enough in order to have a compactness in C1 of your surfaces. Okay. So what people did was to introduce a weaker notion of convergence for submanifolds. So the people typically one will have convergence as measures, and this is very much connected to the notion of currents and varifolds, if you know them. But if you don't know them, they just a weaker notion of C1 submanifolds. The very good thing is that in this weak setting, the area functional is coercive in the sense that having a bound on the area functional is enough in order to have pre-compactness of your sequence. Then one has to prove lower semi-continuity of the area functional under the corresponding weak convergence. And with this approach, one proves the existence of a weak minimizer, so a minimizer with weak regularity. So this minimizer will be either a current or a variable, depending on the approach that you chose. And then all the work is to go back to the smooth setting. So you want to prove, once you have a weak minimizer, you want to prove that this minimizer actually has some good regularity property. So it is C1 up to singular set. You want to study structural properties of these minimizers. Okay, and we would like, and we are very much inspired by this way of doing of classical geometric measure theory. So in classical geometric measure theory, say a weak notion of a C1 submanifold is a current or a varifold or the one that you prefer. Here, what do we have? And why you choose current, varifold, and so on is that because the class of current varifold is closed under weak convergence of measures, which is the right notion of convergence for studying the plateau problem. Here, for Ricci curvature, one starts with the smooth manifolds. One realizes that the right notion of convergence for a smooth manifold with low Ricci bound proposed by Gromov is Gromov-Hausdorff convergence, or we're going to see another very natural one is intrinsic flat convergence. But historically, the Gromov-Hausdorff was the one motivating because it's 20 years older. And one wants to cook up a notion of weak Riemannian manifold with lower Ricci bound, which is going to be the set of CD spaces, which are closed under Gromov-Hausdorff convergence. Okay, and then the idea, as in GMT, is to go back, and then it is to have this kind of abstract machinery, prove result in the synthetic setting, and then try to go back and infer some theorems for smooth manifolds using all this machinery that one has developed. Okay, so this is the rough idea that one has in mind. Okay, Now, the preliminary observation is, say, where to look for weak notions of Riemannian manifold with the lower bounds on the Ricci. Okay. So if you're interested in lower bounds on the sectional curvature, then the good non-smooth framework to look for that are metric spaces, as we briefly touched in previous slides. And this was indeed the point of view of Alexandrov. And that's because the point of view of Alexandrov, as you remember, is that he took Topogonov comparison theorem and he kind of promoted the characterization of sectional curvature as a definition in the metric setting, and that's because the comparison characterization of the comparison triangle makes perfect sense just using distance function. Okay, and the message here is that sectional curvature is a property of the distance, is a property of length, and this is formalized with comparison triangles. What about instead about Ricci curvature? So actually, Ricci curvature is not just a property of length, but it's a property of length and volumes. So if we go back to the previous slide about comparison for Ricci curvature lower bounds, we see that all the theorems there involved a interplay between volume and length. For instance, the Bishop-Gromov volume growth is controlling the volume growth of metric balls. So you need a notion of volume to measure the volume, and you need a notion of distance in order to speak of metric balls. Another basic comparison is the Laplacian comparison. So also there is hidden the interplay between distance and volume, because in order to define the Laplacian, you need how do you find the Laplacian? Typically is via iteration by parts of the gradient squared. So in order to integrate by parts, you need a volume measure to integrate by part. And in order to define a gradient, in order to define the gradient of a function squared, you need a notion of distance to compute the gradient. So also there you have the interplay between volume and measure. And actually, if you look carefully in all the fundamental comparison theorems for Ricci curvature lower bound, there is always hidden the either manifest or hidden the interplay between measure and distance. Okay, so this is just to say that the natural setting for studying lower bounds on the Ricci curvature is not the one of merely metric spaces, but the right setting is the one of metric measure spaces. So you have to endow the metric space also with a reference measure M, which will play the role of volume measure of your metric space. So one choice that we are going to see probably in the last lecture is that if your metric space has some is quite nice and the Hausdorff measure has nice properties, you can choose as M the Hausdorff measure. But a priori, M could be any Borel non-negative measure. It is not, so one choice could be the Hausdorff measure, but you can have thousands of other choices. Okay. Okay. All right. Now, let's go to the non-smooth setting. In order to define the Ricci curvature lower bounds, we're going to see that a key role is played by optimal transport. So in order to do that, let me recall some basics of optimal transport. Before, let me fix some notation. So from now on, I'm going to work with a metric measure space. So more precisely, what is a metric measure space? So XD is going to be a complete and separable metric space. And M is a sigma finite non-negative Borel measure. Okay, so it is a so Borel means that all the Borel sets are measurable. Non-negative means that it is non-negative measure to any Borel set, and sigma finite means the following. It means that, so in more precisely with the sigma finite, I mean that there exists some positive constant A and C, such that for every point and for every radius, the volume of the ball of radius r and center x is bounded by a constant times exponential a r squared. So here what I'm saying is that the volume growth of the magic balls is at most exponential squared. And at this point is only an assumption in the axiomatization, but this assumption is kind of well motivated in the sense that if you have a manifold with the lower bounds on the Ricci curvature, this assumption is satisfied. Okay, and these constants C and A are related to the negative lower bounds on the Ricci. So you are comparing with the hyperbolic space, and this is satisfied. Okay, this is about what is a complete, and this is what this is our notion of metric measure space. And in case the metric space is non-compact, it is useful to fix some reference point x bar and consider the pointed metric measure space, which means the metric measure space with a fixed reference point x bar. Okay. Now, it is useful to consider the space of probability measures defined on the space X. More precisely, if the space X is compact, we just consider all the probability measures. If the space X is non-compact, it is more convenient to consider the space of probability measures with finite second moment. What do I mean? I mean, I consider all the probability measures, so means Borel measures, which are non-negative and with total mass equal to 1, and such that when I integrate the distance squared from the reference point x bar with respect to the measure mu, I get a finite number. Okay, so these are measures which decay at infinity more than quadratically. So that this squared is finite. Okay. Now, with this notation, one can introduce the celebrated Kantorovich-Wasserstein quadratic transportation distance as follows. So consider two probability measures mu1 and mu2 in P2, so with finite second moment. So the distance squared between mu1 and the mu2 in the sense of optimal transport, and the L2 distance between mu1 and the mu2 is the infimum of this cost here in the right. So what is here on the right? We are considering the infimum over what? The infimum over all the probability measures, gamma, in x times x, such that the push forward on the first coordinate is mu1, and the push forward on the second coordinate is mu2. So this gamma is to be thought as a transport from mu1 to mu2. And if this transport from mu1 to mu2 is given by a map, then this gamma is just concentrated on the graph of this map. But in general, we are allowing also transports which are not given by maps. So a priori, the measure at one point in mu1 could split in more than one point in mu2. So you can distribute the measure over point x in mu1 at different points in the support of mu2, and this will correspond to some gamma which is not given by a map. Okay, so all these gammas are possible way of transporting mu1 to mu2. Okay, so now let's go back to the distance, to the Wasserstein distance. So what we are doing is we are taking the infimum over all these transports of what? Of the cost of the transport, where the cost is the integral of the distance squared integrated with respect to gamma. Okay, so we are taking the L2 norm squared of the distance with respect to gamma. Okay, so how to interpret this? What I'm circling here is the cost with respect to the distance squared of the transport gamma, and we are taking the infimum of all the costs of all the ways one can transport mu1 into mu2. Okay, and this is by definition the distance squared from mu1 to mu2. Okay, so one can prove that this W2 induces indeed a distance over the space of probability measure with quadratic with finite second moment, so that the P2 endowed with W2 is a metric space, and this is without any assumption on X. Any metric space would do the job. This metric space is complete if X is complete, and it inherits a lot of nice properties of X. For instance, if X is geodesic, then also the Wahlstein space is a geodesic. Remember that, so my notion of geodesic is kind of the metric one. So a metric space is a geodesic metric space if for any 2 points in X, one can find a length minimizing geodesic connecting the two. Okay. Any questions so far? No. Okay. Okay. So this is the Wahlstein space. Now, in order to speak of Ricci curvature, it is very useful to introduce some functional on the space of probability measures. And such functionals are called entropy functionals. So I'm going to consider a one-parameter family of entropy functionals indexed by a parameter n, which later will be related to the dimension of the metric space. So for finite n,
there is a question on the chat, I guess.
Oh yeah.
Sorry.
Can you read it, please? Because I am sharing the screen.
So the question is, could you repeat your remarks on the gammas?
On the gammas. Yeah. So I don't know which remark, but I will repeat everything so that I don't know which remark. So so these gammas are okay. So what is gamma here in this definition? So gamma is what is called a transport plan from mu1 to mu2. So mu1 and mu2 are two given probability measures. So gamma is a way to transport mu1 into mu2, but a priori in a non-deterministic way, which means that a priori, given some mass over, given that mu1 is given some mass at some point x, you may split this mass into several points in mu2. Okay, so if to which point x in mu1 corresponds exactly 1 point mu2 in support of mu2, this means that this transport gamma is given by a map, which is called a transport map. If instead you are splitting the mass of mu1 in several points, you have just a transport plan. And here, when you define the Wahlstein distance, you consider more generally all the transport plans. Is it good, or was something else?
Seems okay.
Okay. Okay. Okay. Thank you very much. Okay. Good. Perfect. Okay. So let's go. Yeah. So we are talking about entropy functionals. So an entropy functional. So these entropies are functionals which take a probability measure and gives you a real number or plus infinity. Okay. So this parameter n, as I was saying, will play later the role of upper bound on the dimension of your space. But here is just a parameter. It is just a real parameter. Okay. So for finite n, we consider the so-called Riemannian entropy functional. And for n equal to infinity, we consider the so-called Boltzmann-Shannon entropy functional. How they are defined? So as I was saying, we take a probability measure and we want to associate a real number or plus infinity. So let's assume for a moment that this probability measure mu is absolutely continuous with respect to the reference measure m. So here it is key that we are fixing the reference measure m. So then for finite n, the Riemannian entropy functional of rho m is defined by this formula. So I'm taking the density rho. I consider the power 1 minus 1 over n, and I multiply by minus n. So this is a negative entropy. For n equal to infinity, instead, I consider the integral of rho log rho. And this is the famous Boltzmann-Shannon entropy function. And this is if the measure mu is absolutely continuous with respect to m. Now, if instead mu is not absolutely continuous with respect to m, if the parameter n is plus infinity, then we set the entropy to be by definition equal to plus infinity. So, in the infinite dimensional case, if the measure is not absolutely continuous, the entropy is by definition plus infinity. Otherwise, is given by this formula, assuming that rho log rho is in L1. If instead n is finite, then we're going to consider the Lebesgue decomposition of the measure mu with respect to m. So it will have an absolutely continuous part and a singular part. So you just throw away the singular part and you apply this definition to the regular part. Okay. But say, apart from the technicalities of these definitions, what to keep in mind for the rest of the talk and of the lectures is that these entropy functionals are taking you take one parameter n, and given the parameter n, then you have a functional that takes a probability measure and gives you a real number. And here we are all doing geometry, and we're interested in what this entropy functional will tell us on the geometry of our spaces. But let me stress that such entropy functionals show up and actually were introduced in fields which are quite far away from what we are discussing now. So they were introduced in statistical mechanics, thermodynamics, and information theory. So Shannon was interested in information theory and introduced this functional as a kind of measurement of how much information is contained in a string of characters. Boltzmann arrived to an entropy of this kind using, say, studying statistical mechanics and thermodynamics, and Reni as well. So it is kind of amazing how these kind of fields interact one with each other. Okay, so this was about the introduction of these entropy functionals. And now the crucial observation, which is actually a sum up of different works by Cordero, Erasken, Mechanismus, Schläger, Lott-Villani, and Sturm and Voreness, is that if you are given a smooth Riemann manifold, Mg, and you consider the metric measure space naturally associated to it, meaning that you consider D as the Riemannian distance function and as M the Riemannian volume measure, then the Ricci curvature of your manifold is non-negative if and only if the Boltzmann entropy, the Shannon-Boltzmann entropy functional, is convex along geodesics in the vast space. Okay, what do I mean? I mean that what do I mean with the convexity of the entropy along geodesics in the vast space? I mean that for any couple of probability measures, mu0 and mu1 in P2 of X, there exists a W2 geodesic, so a geodesic joining mu0 and mu1 with respect to the metric W2 that we introduced before, such that the entropy along this geodesic is convex. Now, forget for one moment K. So this is just, if you forget K for one moment, this is just the usual convexity of a real function from 0, 1 to R. You are just saying that the entropy functional along the geodesic as a function from 0, 1 to R is convex, which is a kind of beautiful and easy statement to say. If instead you want to characterize Ricci below by K, then instead of, say, just convexity, you have to do a little bit more careful and say that your that your entropy function is k convex along geodesics. With k convex, it means that you have to add up this this extra term, which is known in the literature of convex functions as k convexity. But what to keep in mind is that lower bounds on the Ricci are equivalent to convexity properties of the entropy along geodesics in the Barstein space. Now we can do the same trick as Alexandrov did for Alexandrov geometry, because in Alexandrov geometry, the point of view of Alexandrov was, well, I have Topogonov theorem, and I observe that the right-hand side of Topogonov theorem, so this characterization via triangle comparison, makes perfect sense for a metric space, and then I can just define a metric space with lower bound on the sectional curvature by saying that this characterization via triangle comparison holds in metric spaces. Here we observe that this notion of convexity of the entropy along geodesics in the Barstein space makes perfect sense in a non-smooth setting. It makes perfect sense in the setting of metric measure spaces. And here notice that we need, so it is not just metric space, but metric measure spaces, because when you define the entropy functional, it is key that you are fixing also the reference measure, because if you remember, you are considering probability measures which are absolutely continuous with respect to a reference measure, and all the formulas really make use of the reference measure n. Okay, so this notion of convexity of the entropy makes perfect sense in a metric measure space. And then the idea of Lott-Sturm and Villani is to say that by definition, your metric measure space has non-negative Ricci curvature in a synthetic sense if the entropy functional is convex along geodesics in the Barstein space. Okay, so this is what I just said is the condition CD 0 infinity, which is convexity of the Shannon-Boltzmann entropy along Barstein geodesics. If you want to make sense of lower bounds on the Ricci by k, but you're not interested in an upper bound, so CDK infinity, so lower bound on the Ricci by k, but not upper bound on the dimension, then you have this k convexity of the Shannon-Boltzmann entropy. If instead you want to make sense of a lower bound on the Ricci by k and upper bound on the dimension by n, instead of the Shannon-Boltzmann entropy, you consider the Riemannian entropy, and you have to be careful in writing down the correct convexity condition. Here I'm not doing it, so it is kind of a distorted Kn convexity, but from the say conceptual point of view is not different. So it is only a right way to express the right notion of convexity of the entropy of the Riemannian entropy along Barstein geodesics. And the idea of how to get this is you study what happens in the model spaces, and then you inherit the inequalities in the synthetic setting. Okay, so this is the rough picture, and so these spaces are called CDKN. So CD stands for curvature dimension condition. Kn, K is the lower bound on the Ricci curvature, and such a K is any real number given. And N plays the role of upper bound on the dimension and is any real parameter from 1 to infinity. Plus infinity is included. So it's, you can also have CDK infinity. Okay, so is there any question about the definition?
I have one. In what sense do we consider the dimension? Is it the dimension if we go back to the Riemannian setting, or?
Okay, so all right, this is a very good question. I'm going to be a bit, I'm going to be more precise later. So at this moment, it is just an axiomatization. So so in this definition, there is no Ricci and no dimension. So I'm just telling you how to interpret K and N, but in this definition, K and N are just real parameters. What you prove, what you prove out of the definition is that the Hausdorff dimension of a CD Kn space is bounded above by n, and this was proved by Sturm. Okay, but this is something that you prove a posteriori. So you take the definition, and then working from the definition, you prove that a metric measure space which satisfies CD Kn has Hausdorff dimension bounded above by n. So such an n must be thought of as an upper bound on dimension. Okay.
Thanks.
Andrea, there is also a question on the chat.
Yeah.
In the same spirit, I guess you almost answered.
Is the measure parameter that goes to infinity in a similar fashion as thermodynamic limits in statistical mechanics? How comes to Riemannian manifold? We look to n equal to infinity. Okay, so in the Riemannian, okay, I'm going to touch this later and also in the next lectures, but it's good to mention it here since we have this question. So for a moment, I just spoke. I just considered Riemannian manifolds with the volume measure, but as I was saying before, M could be any Borel measure. It is not necessary the Hausdorff measure. So also in a Riemannian manifold, you can consider the volume measure, and then you can multiply the volume measure by a function, by a non-negative function. You get another volume measure, which is weighted. And this is the classical sense of, this is the classical setting of weighted Riemannian manifolds. On weighted Riemannian manifolds, you have a slight variation of the Ricci tensor, which is the so-called Buckley-Emery Ricci tensor. And in this Buckley-Emery Ricci tensor, you have also a parameter n, which plays the role of, again, upper bound on the dimension. But in a synthetic sense, in the sense that you can have an n-dimensional manifold like Rn, okay, and you can endow Rn with a measure, for instance, the Gaussian measure, and this weighted space will satisfy CD1 infinity, but not CD Kn for any n. Okay, so if you endow also a smooth space with a weighted measure, then from a point of view of Ricci curvature, from a point of view of functional inequalities, it behaves more as an infinite dimensional space than a finite dimensional space. So this n must be really thought just as an upper bound on the topological, on the Hausdorff dimension, and has to be thought as what you see from functional and geometric inequalities when you prove them using Ricci curvature. Okay, so even on a finite dimensional space like Rn, you can put some structure which looks like infinite dimensional from a point of view of functional inequalities like Gaussians. Okay, you need that m is the Hausdorff dimension for a bound. Okay, then, okay, I think that this answered the question about the thermodynamic limits and statistical mechanics. Then is another question by Erwan Obri. So you need that the measure m is the Hausdorff measure for the bound in the Hausdorff dimension? No. So the bound on the Hausdorff dimension is true for even if m is not the Hausdorff measure. So when you have yeah, that's it. And this is proved in the paper by Sturm. This is basically the rough idea is that CDKN with finite n will imply Bishop-Gromov volume comparison. With Bishop-Gromov volume comparison, you have uniformly doubling, and then you can start covering your space with balls and use a kind of covering argument to prove that the Hausdorff dimension is bounded above by n. This is the rough idea. Any more questions? Did I answer to the questions? Is everyone happy?
Yes.
Okay, good. All right. Okay, then just to summarize, so to keep in mind is that this CDKN condition, again, is a definition of Ricci curve bounded below by K, and dimension by above by n in an intrinsic axiomatic way for metric measure spaces. So K and N are real parameters. And the rough idea to keep in mind is that the more convex is the entropy functional along geodesics in the Wassler space, the more the space is positively Ricci curved. Now, some good properties, as someone asked, is what happens when one compares with smooth manifolds. So this notion is consistent in the sense that the manifold MG satisfies CDKN if and only if the Ricci curvature is bounded below by K and the dimension is bounded above by N. But here, let me say that here I'm fixing, when I say this, I am considering the as M as reference measure, the volume measure of the Riemannian metric G. If instead you consider some weighted measure, you can say vary this upper bound N. You can increase it or even decrease it. As we are going to see in the next lectures more in detail, this CDKN implies several, basically most, or if not all, of the geometric properties that we know and love in comparison geometry for smooth manifold. Here, let me just mention a few. So one can prove Brun-Minkowski inequality in the setting of CDKN spaces. One can prove the Bishop-Gromov volume growth. One can prove diameter bound by Bonnet-Myers, Lignov spectral gap, and so on. But in the lecture of today, let me focus on the stability. So what can we say about the stability of CD condition? So is the CD condition stable under convergence of metric measure spaces? So meaning if I have a sequence of CDKN spaces which are converging in measure-of sense to a limit metric measure space, is the limit CDKN as well? So this question is kind of key in this program that I was recalling, because if one proves stability, in particular, one will get that Ricci limits are steady spaces, because combining the consistency with the stability, so the consistency will tell that a smooth manifold with lower bound on the Ricci are CDKN. If we prove that the class of CDKN spaces is closed under measure-of convergence, it will imply in particular that limits of smooth manifold with lower bound on the Ricci are CDKN spaces. Okay, now stability, let me briefly recall the setting and the results. So there are, as probably you know, this approach to CDKN spaces was done in three independent papers, two by Sturm, one on CDK infinity and one on CDKN, and which are on ACTA, and one paper by Lott-Villani, which studied both CD0N and CDK infinity. And they had several similarities, but also some differences. In particular, there was some difference in the stability. So they consider different notion of convergence and different assumptions. Here, let me briefly recall what they do and what are the advantages and disadvantages. So Lott-Villani worked in the framework of proper spaces. So what is a proper space? A proper metric space is a metric space where bounded closed sets are compact. So any closed ball is compact. And they proved that the CDKN condition is stable under pointed measure Gromov-Hausdorff convergence. So meaning that so what is a measure of pointed measure Gromov-Hausdorff convergence? Mean that for every r bigger than 0 is a measure of Gromov-Hausdorff convergence of balls of radius r around the given points of the sequence of spaces which are converging. Okay. Instead, Sturm studied the stability under a different notion of convergence, which require the reference measure to be a probability measure with finite second moment. So Sturm is working in the setting of probability spaces with finite variance, meaning that the reference measure M is a probability measure with finite second moment. And on this class, of measure spaces, he defined a distance, which is also known in the literature as Gromov-Hausdorff, which basically is, I think it's like the term Gromov-Hausdorff is quite suggestive, because like Gromov-Hausdorff is you have the Hausdorff distance and you make it a distance among metric spaces. How? By considering isometric immersions in an ambient space and then taking Hausdorff distance there. The Sturm or Gromov-Hausdorff distance has the same kind of underlying idea. So you have metric measure spaces, x1 d1 m1 and x2 d2 m2. You consider isometric immersions in an ambient space, in any ambient space, which is a metric space, and then you take the Hausdorff distance between the push forward of the first measure and the push forward of the second measure. Okay, so more precisely, what you're doing is you consider all complete and separable metric spaces Z and all possible isometric embeddings iota of from the support of mu1 and support of mu2 in this ambient space Z. You consider the Hausdorff distance between the push forward via this isometric embedding of M1 to the push forward via the isometric embedding of M2. These are two still measures with the finite second moment, because I1 and I2 are isometric embeddings, and M1 and M2 are in P2. So here you are in good position to define the W2 distance, and it is the W2 distance in the ambient space Z. Okay, so this is a well-defined number. And now you take the infimum among all the possible ambient spaces and on the possible isometric embeddings in the same kind of frame of ideas as Gromov-Hausdorff. Okay, so this was the distance introduced by Sturm, and Sturm proved that under this notion of distance and notion of convergence, the CDKN condition is stable under this deconvergence. Okay, so Lott-Villani, stability of CDKN under pointed measure of Hausdorff convergence, and Sturm stability under this convergence or Gromov-Hausdorff convergence. Okay, now what happens in for the infinite dimensional case? So when while in the CDKN case for n finite, the CDKN condition implies properness of the space. This is from Bishop Gromov. So Lott-Villani fully covers the situation. When n is equal to plus infinity, CDK infinity does not imply any sort of compactness, not even local, of the space. For instance, you can have an example of CDK infinity spaces which are really infinite dimensional, like linear space or really say, Hilbert spaces and so on. Okay, so in this setting, the pointed measure of Hausdorff convergence is not really the natural convergence, because the Hausdorff, so this you probably used to know a little bit of Hausdorff convergence, but say Hausdorff convergence is a very good convergence among very good notion of distance for compact sets of an ambient space. If the sets are not compact, you can still define it, but it's really a bit too strong. Right. So so bringing this to the Gromov sense, so the Gromov-Hausdorff distance is a very natural notion for compact metrics for compact manifolds or compact metric spaces. The pointed version, so the pointed Gromov-Hausdorff convergence, is very natural for spaces such that the balls are compact. But if you are in a truly infinite dimensional situation where the balls are not compact, it seems a bit too strong. Okay. All right. So in the CDK infinity, so Lott and Villani fully covered the situation for CDK n, for finite n. For CDK infinity, probably it is more natural to consider the approach by Sturm. So this approach which covers the situation of spaces with the normalized measure. But in some geometric situation, the assumption that the reference measure is a probability measure with the finite second moment is a bit too restrictive, in the sense that when one study blow-ups, like blow up meaning that you are studying the tangent cone at a point, so you are taking your space and you are dilating more and more and more, and in the limit you expect to see Rn, and Rn, of course, is endowed with the Lebesgue measure, and the Lebesgue measure is not finite, so you are going out of your setting. Or when you study blowdowns, when you want to study the tangent cone at infinity, so you are a non-compact manifold and you want to understand how it behaves at the infinity. I've seen that, I think that you've seen a lot of that last week in Gromov hyperbolic spaces. What you do is you do a blowdown to study what happens at infinity, but also here, if typically your space is infinite measure and the blowdown also, you expect to have some homogeneity and still having infinite measure, and so you would not like to assume the measure m to be a measure of a probability measure with finite second moment. Okay, so this is just a motivation because to say that one may like to consider sequences of spaces where the measure is not of probability, and then maybe one may also be interested in considering sequences of manifolds which have diverging dimension. So maybe the dimension is not fixed, but it is diverging. And in all this, and in these last two settings, say the previous two convergences seem to be a bit restrictive. So the question is, what is a natural notion of convergence in these situations? And the second question is, once we have a natural notion of convergence, is the CDK infinity condition stable with respect to such a notion of convergence? Okay, so in order to answer the first question, one possible proposal was in a paper with Gigli and Savarè, where we consider what we call the pointed measure Gromov convergence. So this is inspired by Gromov. So we still have embedding in ambient spaces, in ambient metric spaces, but instead of considering the convergence in W2 as Sturm was doing, we just consider the weak convergence of the push forward of the measures. And this will give a good notion of convergence of the spaces themselves. Okay, so let me be a bit more precise. So we have a sequence of pointed metric measure spaces, xn, dn, with reference measure n and reference point x bar n. We say that they converge to the space x infinity with all the infinity things in the pointed measure Gromov sense if there exists a complete and separable ambient space Z. So this, you have to think Z as a kind of big complete and separable space, and isometric embeddings iota n from xn into Z. So what you should think is that this ambient space Z is containing isometric copies of your spaces xn for all n finite up to infinity, and such that when you consider the push forward of the measure mn via these isometric embeddings iota n, you have weak convergence of these measures to the push forward of m infinity with respect to the isometric inversion iota infinity. What do I mean with weak convergence? I mean weak convergence in duality with continuous functions which are bounded and with bounded support. So reading the formula is that for any function which is continuous, bounded and with bounded support in the Diamond space Z, you ask that the integral of phi with respect to the push forward measure of Mn is converging to the integral of phi with respect to the push forward measure M infinity. Okay, so from the definition, one critique to this definition that you may ask, that you may address, is that well, the definition looks a bit extrinsic, so it is making use of an ambient space Z where all these Xn are isometrically immersed, are isometrically embedded. So the question is this notion really well defined? Is this notion kind of intrinsic? And the answer is yes. And indeed, this notion of convergence can be characterized in a maybe less immediate way, using some totally intrinsic notions according to various approaches. In this paper with Gigli and Savarè, we proved that this notion of convergence is completely equivalent to a pointed version of the Gromov reconstruction theorem, so of a notion of convergence based on Gromov reconstruction theorem, or via a pointed weighted version of Sturm d distance. Okay, so one should think of this notion as a kind of generalization of Sturm d distance when your measures are not probability and with finite second moment. Okay, now this notion is kind of consistent both with Lott-Villani and with Sturm, because on doubling spaces, this pointed measurement of convergence is equivalent to measure Gromov-Hausdorff convergence, so it is completely equivalent and consistent with the approach by Lott-Villani. And if the measures M, N are in P2, so if they are normalized with finite variance, then this pointed measurement of convergence is equivalent to Sturm deconvergence. So it is so this approach is consistent with the Sturm approach. Okay, but the advantage of this pointed measure Gromov convergence is that it does not need any assumption on the spaces Xn, Dn, and M. So they could be no finiteness assumption, no local compactness, their dimension could blow up, there's no assumption. Okay, so this looks like to be a kind of natural notion of convergence, a natural extension both of Lott-Villani and of Sturm approaches to say, convergence used by them. But the question now is the CD condition stable with respect to this notion? So in the finite dimensional case, by the consistency, just by Lott-Villani, you have that the CDKN condition is stable under this notion of convergence. But what about the CDK infinity condition? Is it stable under this notion of convergence? And the answer is yes. And it was proved in this paper in collaboration with Gigli and Savarè. So we proved that if you have a sequence of CDK infinity pointed multi-measure spaces, so let's call them Xn, Dn, Mn with reference points x bar n, which converge to a limit space x infinity, d infinity, m infinity with reference point x bar infinity in the pointed measurement of sense. And if your sequence of spaces Xn is CDK infinity, then the limit is CDK infinity as well. Okay, so I feel I'm already out of time, so I will briefly sketch this proof and then I will end. I think it's a good moment to stop after this sketch. Okay, so let me just discuss a brief sketch of the proof, which is so the line of proof is borrowed by is the same, is borrowed from both Lott-Villani and Sturm. So the kind of basic scheme of argument is common, then the technicalities are quite different, and the more you go general, the more you complicate your life in proving that things are really as you wish. But say, let me just give you a sketch of what are the main steps in the proof. So the first step in the proof is to show what is called gamma convergence of the entropies along under the pointed measure Gromov convergence. What do I mean with gamma convergence? This is kind of classical notion of convergence in calculus of variation. So and it is quite powerful because it is usually related to, so when you have gamma convergence of functionals, this is kind of a it is very much related to having convergence of minimizers to minimizers and minima to minima. Okay, so when you have convex functionals, it is really the kind of natural notion of convergence. So this gamma convergence typically consists in two steps. One is the so-called gamma Lie-Minf inequality, which is as follows. So you ask that for any measure in the limit space, any probability measure with finite moment in the limit space mu infinity, and every sequence mu n in the space Xn, such that mu n is convergent to mu infinity weakly in this ambient space Z, which is containing everything, it holds that the Lie-Minf, it was like a kind of lower semi-continuity. So you ask that the limit entropy of the limit measure with respect to the limit reference measure is less or equal than the Lie-Minf of, sorry, here is the typo, un. So here is the entropy of the n-dimensional, sorry, this is correct. It's U infinity is the Shannon entropy. This is the Shannon entropy is the entropy of the approximating measures mu n with respect to the reference measure mn. Okay, so this is the gamma Lie-Minf. And then the other part of the gamma convergence is what's called the existence of a recovery sequence, which means that for every limit measure mu infinity, you want that there exists a sequence of measures mu n in P2 of Xn, which converge to mu infinity weakly in Z, and where you have the other inequality, where you have kind of upper semi-continuity, kind of. So you want that the limit entropy of the limit measure with respect to the limit reference measure, here is mu infinity, not mu zero infinity, sorry, here is the typo, is bigger or equal than the lim sup of the approximation, the lim sup of the mu n measure with respect to the mn reference measure. So putting the two together, so not only that, putting the gamma Lie-Minf and the existence of a recovery sequence, you get that for every measure mu infinity, you have a sequence of approximations mu n, such that the entropy of mu n is converging to the entropy of mu infinity. Okay, so this, so the idea is that. Okay, so this is the gamma convergence. Then the second step is we know that the measures mn are converging weakly, so we have some compactness at the level of mn, and this compactness at the level of mn is enough to prove compactness of Wahrstein geodesics in the converging spaces. So here, what do I have in mind? So we have our sequence we have our sequence Xn, which is CDK infinity, which means that we have the convexity of the entropy, and we want to show that X infinity is also CDK infinity. So we want to pick two measures in X infinity, so say mu zero infinity and mu one infinity, and we want in the end construct a geodesic joining the two such that the entropy is convex along this geodesic. So what is the idea here? Is we have this approximation of X infinity by the spaces Xn, and by using this gamma convergence, we can apply the recovery sequence to mu zero infinity and mu one infinity. So we get an approximation of mu zero infinity and mu one infinity by measures, say mu zero n and mu1n, such that the entropy at the endpoint is converging. This is by the recovery sequence. Now, using that xn is CDK infinity, we can construct for every n a Weisstein geodesic joining mu 0n with mu1n, such that the entropy is convex along this Weisstein geodesic. Okay. Now, with step 2, I claim that we have enough compactness in order to pass the limit in this Weisstein geodesic. So I will have a limit Weisstein geodesic connecting connecting the two limit measures, connecting mu0 infinity and mu1 infinity. And using the gamma limit inequality, I have that the convexity is preserved, because convexity is basically that the intermediate point is below the finite point. So using that in the middle of the geodesic, the entropy can just go down, you will be maybe more convex than before. And so you can pass the limit and conclude that the K-geodesic convexity is preserved. So this was just a sketch. Of course, if you want to fix all the details, these are pages. But yeah, it was just the geometric picture behind. So I think that my time is over, or of 10 minutes. So sorry for being over time, and thank you very much for your attention.
Thank you, Andrea. There are a couple of questions on the chat, which I did not mention. I was waiting for the end of your
so let's have a look. Okay. Okay. So what is the meaning of more? Okay, right. So before, so what is the meaning of more convex with respect to the entropy functional UNMs? Yeah. So in the previous slides, yeah, here I think when I was mentioning the CDKN, I was saying that yeah, here what I mean is that if you want, let's consider just an example. Then I'm going to being more abstract. So consider the case of non-negative Ricci. So non-negative Ricci is telling you that the entropy functional is convex. Okay, so you have this convexity inequality. Now, when I say that positive Ricci means that your entropy is more convex, I mean that if K is strictly bigger than 0, okay, here notice that what you're doing, you are taking you are subtracting a positive term. So this K now is positive. So this means that your inequality, so that the right hand side is lower. So your convexity, you are asking a more stringent notion of convexity. So in this sense, I'm just saying that positive curve. So if K is strictly bigger than 0, you're asking that your entropy is more convex, is a stronger convexity condition than with K equal to 0. So, and in this slide, I was saying that the more convex is the entropy, meaning that if you are convex in a stronger sense, this corresponds to Ricci-curvature lower bound by K and K bigger. So if you are more convex, then your Ricci is bounded below by some bigger K. Does it answer the question? Is it more clear, Julian? Okay, I see no reaction, so I guess so. Then there's another question by Anshen. So if mu0 infinity, or is it mu0 infinity, or mu0 infinity is yeah. Thank you. Yeah, that was that in the proof it was a typo. Yeah, as I was saying during the proof, here is a typo, and when I will send the slides, I'll make sure to correct it. Yeah. So here, because when I was typing it, I wanted to type what I said in words. So I wanted to say mu0 infinity, mu1 infinity, but then the slide was becoming a mess, and then I just simplified it, and but then something remained. So this is mu infinity and mu infinity, and not mu0 infinity. I will correct it when I send the slides around. Thank you. Any more questions? Yeah. Are these entropy functions related with the volume entropy? Which volume entropy you mean? The volume entropy in the for negative the one of hyperbolic geometry? I guess so. Yeah. Thank you very much. Volume entropy, so there is no reaction. So I think that volume entropy, I guess the one in the theorems by Besson, Courtois, Gallot, I think these are, yeah, that one. Okay, good. Yeah. So there is some connection in the sense that you can generalize some of these beautiful theorems also to the setting of RCD that we're going to discuss in the next lectures. RCD spaces with lower bound, with negative lower bound on the Ricci curvature, and this was recently done by a team across US and Mexico. There was Perales, Gu Fan Wei, and other 5 or 6 co-authors. So in sense of there is some connection, but I'm not aware of any kind of quantitative connection, say, in the sense that, say, it is not, I'm not aware of saying of something like you can bound from above and below, or something like that, the volume entropy in the universal cover with the Shannon entropy, also because they relate also with kind of different objects. So the Shannon entropy is the entropy of some probability measure with respect to some volume measure. The volume entropy is something which takes care of how takes care of the geometry of the universal cover and how the fundamental domains say spread in the universal cover. So yeah, probably there is some connection, but it's not so clear to me. It's kind of the precise connection. If there is, so it's not. What is clear to me that there is some connection, and there is some theorem proved in that setting, in the sense that Ricci lower bound, in the sense of entropy convexity of the entropy, are connected also to the volume entropy of the universal cover for a negative n. But if you ask me a precise connection of the two, it's not so clear to me if there is one. But it's interesting to
not clear to me either, actually. Okay, are there any other questions in the room, maybe? No. People are very hungry in the room now.
Oh, yeah, right, because you are 1 hour more. Yeah, sorry for keeping you there.
In any case, I thank you very much for this beautiful introduction. And if I remember well, we see each other tomorrow, same time. Tomorrow morning, yeah. Thank you very much for your attention. Okay, thanks, Andrea. See you tomorrow. Bye-bye. See you tomorrow. Bye-bye. C'est bien.